Hi everybody. In this video we're going to look at metamorphism and tectonics, and in particular we're going to look at two diagrams from a very nice book by Gary Ernst published in 1976 called Petrologic Phase Equilibria. It's one of my favorite textbooks, and in this particular book on pages 253 and 252 there are two figures that are amongst my favorite in terms of understanding what metamorphism means, the way we can use metamorphic identifications to better understand plate tectonic setting. And you can see that here. So here in a previous video, we looked at identifying metamorphic facies through the Escola diagram, where in a plot of pressure versus temperature, so we have, let's say, temperature increasing to the upwards and pressure to the left, we can map out certain areas where we have certain kinds of metamorphism. So we would have zeolite metamorphism down here. At higher temperatures, we would go into green schist, amphibolite, and then granulite facies metamorphism. Well, what this diagram does is it allows us to put a tectonic template on top of those identifications that we make in the field or through thin sections. So for example, where do we find blue schist metamorphism? Well, we can go anywhere where we see a 3. Over here, there are no 3s. This is a cross-section of a mid-ocean ridge, and you'll see that we have a 5 and a 6 and an 8. There are no 3s. Well, what's 5, 6, and 8, 7, and 8? That's green schist through granulite grade metamorphism, so we can get very high temperature metamorphism. We don't get the very cold high pressure metamorphism that would characterize the blue schist facies. So if we found, let's say we're doing some field work here at the surface on some arbitrary place out in the field, and we find blue schist metamorphism, we would know that we are not looking at an ancient mid-ocean ridge. There's no place where blue schist metamorphism would happen. The only place we find it here, where we have a subduction zone, in this case it looks like it's, well, it could be anything. It looks the way it's drawn. It could be continental crust. But the only place we find the 3s are in this subduction zone area here, pretty close to the subduction zone interface where this downgoing slab is coming into contact with the mantle wedge. The mantle wedge is this part of the mantle here. So this is the crust. The crust is this part here, and this is the mantle that's wedged between the crust and then the downgoing slab. So we call it the mantle wedge. So if we found blue schist facies metamorphism here in some ancient rocks, we would know that at one time in the past, when those rocks were formed, they were part of a subduction zone, and we can begin to recreate the tectonic environment based on those kind of metamorphic conditions. Let's take a look at something else. Let's find green schist facies metamorphism. Where does green schist facies metamorphism occur? Well, over here at the mid-ocean ridge, it occurs at this depth here, and then over here in this continental setting, the 5 looks to be this zone here. Notice that we have to go pretty deep to see green schist facies metamorphism in the forearc, and also pretty deep in the back arc area here. But we hit this region of green schist facies metamorphism at much shallower depths here. Why is that? Well, remember from our previous diagrams, green schist facies metamorphism is very highly controlled by temperature, not so much pressure, but temperature. And all this black material here, that is magma. There are fluids that are being ejected from the subducted slab, invading the mantle wedge. That water and other kinds of volatiles like CO2 can help lower the partial melting temperature of the peridotite that makes up the mantle wedge, so it causes melting. Those melts rise up into the crust, and as they rise into the crust, they carry a lot of thermal energy with them, and they're dumping this thermal energy into the crust. And so when we see these boundaries between green schist and amphibolite and other facies rise upwards in this area of the volcanic front, we're really mapping isotherms. This is the isotherm that separates the boundary between 6, which is epidote amphibolite, and 5, which is green schist facies metamorphism. And those thermal boundaries are perturbed upwards as we dump heat into shallower and shallower depths. We get hotter temperatures at shallower depths when we're in the volcanic front, where we're getting a lot of magma pumped into the crust. Anyway, the bottom line with these diagrams, the reason I like them so much, is they give us a framework for taking what we identify in the field and in thin section, these various metamorphic facies, and then putting them into a tectonic template. So if we're looking at some ancient rocks out here, anywhere on Earth's surface really, we're able to use this kind of diagram to reconstruct the tectonic environment. And it can be very powerful, not just on Earth, but on Mars. If we start mapping metamorphic facies on the surface of Mars, we could figure out what kind of tectonic environments existed on Mars. Did Mars ever have subduction? Well, if we find blue schist facies metamorphism on Mars, then we'll know that it did at one time probably have something like Earth's modern plate tectonics with subduction zones. On the other hand, if blue schist facies metamorphism is absent, it might mean that it was always a stagnant lid. And who knows what metamorphic mapping of the surface of Mars would reveal, but it's probably one of the most important things we can do in the study of planetary sciences. It probably is even more important than our current obsession with trying to find bacteria, because understanding those plate tectonic conditions, which we will gain by looking at these metamorphic conditions on places like Moon, Mars, Venus, Mercury, and other planets, they'll tell us about the geologic history that might allow life to evolve or prevent it from evolving. Anyway, if you have a chance, take a look at this textbook, pick up a copy if you can, and definitely take a look at these figures as you're studying metamorphic petrology.